Hello, let's do a quick guide of the equation booklet that will be in the exam with you. The equation booklet contains a lot of useful information. So I'll be going through it, highlighting any laws using red pen, any definitions using green pen, any origins where needed, where the equations come from, literacy in pencil. I'll be highlighting energy using a pink highlighter. I'll be highlighting forces using a green highlighter, and some acceleration. Here we have a little section on cosmology. At the top we have the Doppler Effect, which allows us to determine the velocity of a galaxy compared to its motion compared to the speed of light, and that will cause a change in the frequency of the light that we're seeing from the galaxy. Usually you'll see like absorption spectra across the spectral absorption lines, and where those lines appear allow us to determine whether it's red shifted or blue shifted. The change in frequency caused by the motion will mean that the red shifted spectra we see will have a frequency that is lower, so you'd be subtracting the frequency from the normal in the lab reference frequency. For blue shift, the frequency will be higher because you'll be adding on the change in frequency there. For the wavelength, it'd be a similar story. You'd have your reference wavelength, and for redshift, you would take that reference wavelength and add on more due to the motion of the galaxy. And for blue shift, you would take the reference wavelength and subtract the change in wavelength due to the motion of the galaxy. The next equation is used for determining distance in parsecs, short for parallax seconds. The one at the top is 1 arc second. 1 degree is a 1 degree, 1/60th of a degree is a minute, and 1/60th of a minute of a degree is a second. So 1 second is a 60th of a 60th of a degree. And then this here, D at the bottom, would be called the Stellar Parallax from Earth in arc seconds. And what that means is if we are orbiting the Sun, and this is the Earth as it goes around the Sun, we would observe a star in the distance and compare it to stars in the mega distance, and as you view the same star in comparison to that background from different places in our orbit around the Sun, it will produce this angle here, which is our parallax angle, and that's the angle that will then go into this equation. It effectively comes from knowing that this distance between the Earth and the Sun is around about 1.5-ish, I think, times 10 to the 11 meters. And if you needed to convert a distance in parsecs to a distance in meters, you would use a bit of trig in order to achieve that. So I'll try and write that over here. That would be tan of the parallax angle equals opposite over adjacent. That's going to be 1.5 times 10 to the 11 meters divided by, we'll call that x, and we'll say that the distance here from the Sun to the star, or from us, pretty much the same there, would be x. I suppose we could have done sine, it wouldn't make a difference either way. So if you rearrange this to get a value x for the parsec, it would be 1.5 times 10 to the 11 divided by tan of 1 divided by 60 squared. 60 squared because it's minutes and seconds. And that should give you a distance of 3.1 times 10 to the 16 meters. The next one down is Hubble's law. It would be recessional, as in moving away from your velocity. All galaxies are moving away from us. The velocity at which galaxies are moving away from us is directly proportional to their distance from us. So the further away the galaxy is, the faster it's moving away from us. That's because the further away you look, the further back in time you go. The further back in time you go, the faster the universe was expanding. Oddly, the distance would be measured in megaparsecs, and the velocity, oddly as well, measured in kilometers seconds to the -1. It's just convenient that way. Consequently, the unit for Hubble's constant is measured in kilometers per second per megaparsec. And so if you're going to use the equation below, which would be used to determine the age of the universe, you would first need to convert Hubble's constant from kilometers per second per megaparsec to seconds to the minus 1. And then that would produce the age of the universe in seconds to the minus 1, but then you'd usually convert that into billions of years. Up in the corner here, I think it's worthwhile using some of this information to quickly work out what we call the critical density of the universe. And the critical density determines whether it's open, closed, or flat universe, and that is going to be determined by whether it has enough kinetic energy to overcome gravitational potential energy or whether it doesn't. So I suppose we could put in half mv squared for our kinetic energy. We could put, I suppose, mgh in for our gravitational potential energy, but really we need to make some adjustments to make them more appropriate for their application in the universe. So the first thing I'm going to do is instead of half mv squared, we're going to go a half m, and instead of writing v, I'm going to be writing Hubble's constant times distance. So that's going to be Hubble's constant squared. But instead of putting d for distance, I'm going to put radial distance r squared, because then that would fit in with our more grown-up version of gravitational potential energy, which would be big G, big M, little m over r. And what will happen under these circumstances is the little m's would cancel. Big M would be the mass of the entire universe, and because we don't really know that, we would like to substitute in density equals mass divided by volume. The volume of the universe we'll assume is a sphere, 4/3 pi r cubed, which means that I can rearrange this and say that m equals 4 rho pi r cubed over 3, and pop that in for the mass of the entire universe, and that will, with a bit of rearranging, will give us the critical density of the universe. Rearranging to make rho the subject of the universe depends on two constants. One is Hubble's constant, the shakest constant there is, divided by 8 pi capital G Newton's law, the gravitational constant. So that little derivation is quite handy there. Practice this one yourself.